Welcome to Ecos by Jigyansa. Hi, I am Veer. Today we will discuss about the molecule that self-assemble and the chemistry that build intelligent structure with the world of supramolecular chemistry with Professor P.S. Mukherjee.
Professor P.S. Mukherjee is a recipient of prestigious Shanti Swarup Bhatnagar Award for his contribution towards the field of chemical sciences.
So, let's begin.
Hello, sir. Welcome
Hi.
to the podcast. Could you take a few minutes to explain what your research is about?
Okay, my research is on self-assembled discrete architectures that have definite shapes and sizes. Our main focus is to develop water-soluble such architectures that are having hydrophobic pocket. Challenge is to use such water-soluble discrete architectures as molecular flask or vessel to study limitless chemistry in their confined pocket. So it is not restricted that we have to study this. Whatever chemistry is known in the literature or in textbook, we try to repeat such chemistry or study in confined molecular pockets to see how different is such chemistry compared to conventional known chemistry that is known in the textbook or in literature.
So, what first inspired you to pursue supramolecular chemistry, and how did your early career shape your research direction?
Okay, so I did my PhD on coordination polymers of particularly copper to metal ions, including their magnetic studies. So in synthesis of such coordination polymer, it was very difficult to predict the exact geometry. Rather, those were mostly serendipitous synthesis. That is why I wanted to change my field to have desired structures so that we can really tune the properties and function based on our need. And this is how I got into supramolecular chemistry, particularly using metal ligand stronger and highly directional interaction so that one can really design architectures of shapes that we want.
So, for someone outside chemistry, how would you explain what a molecular cage or a molecular container actually is?
A molecular cage or molecular containers are molecules that have closed shape structure, but still they have some windows for any foreign molecules to go inside the pocket. So they can be used as containers either to store or to study chemistry or for chemical reactions, transformation. So they are basically chemical entity with defined shapes and sizes, and they have some entry and exit pathways for the reactants or substrates or chemicals to go and then come out. So they are container molecules.
So, your group often talks about self assembly. And why is nature so good at it, and what can scientists learn from it?
Self-assembly means it is an organized way to assemble molecules. So it has a particular pattern. So from a chaotic system to self-assembly. So nature generally doesn't allow self-assembled system because nature always prefers randomness or where entropy is more. But this organization or self-assembly is actually opposite to that nature's event, but we use other thermodynamic parameters like enthalpy and others to organize them. So from a chaotic system, if you can make system in order, then of course it is good. It is good for life also. Instead of your random life, if you have a systematic methodical life, then it is always beneficial. It is true for students and for individual life.
So, what part of running a research lab gives you the most satisfaction? Teaching students, or designing molecules, or discovering something new?
I like all, first of all, but of course discovering something new is always challenging. That I like most.
How do you stay creative in a field that constantly evolves and at the same time it is most competitive?
see, my principle is slightly different from many others. Many others always think to have something new, exciting, but what I do, I try to just repeat same chemistry that is known in textbook for a long time in a non-conventional way to show to the community that it is always not true in this way. We can do in a different way and that will be different, result will be different. And that's why we can compete with others like chemistry. As I said, organic chemists always try to study chemistry in organic solvent. So we repeat same reactions in aqueous medium in a non-conventional approach. Try to show that chemistry in confined space, particularly in molecular vessel, is different from conventional chemistry that is known. And that's a unique part of our research. And that's why we can also publish in competitive journal, compete with our counterparts.
So your group has published several impactful papers. Is there one result or project that you personally most proud of it?
There are many interesting chemistries, but I think, in my opinion, most interesting result that we got was, instead of doing chiral resolution or separation of chiral compounds, convert enantiomers to a single enantiomer. That is really challenging work that we have developed. And that is useful. Many groups have actually used such thing. So instead of doing traditional chiral resolution that organic chemists do to separate chiral compounds from a racemic mixture, we could actually convert chiral cages to a single enantiopure cage without separation, without any product loss or anything. And that is really challenging and useful.
So where do you see supramolecular chemistry making the biggest real-world impact in the next decade?
In many ways, for example, enantioselective catalysis. Organic chemists have been designing many organic catalysts or chiral catalysts to develop, to actually obtain a product in an enantioselective manner. So if you can do same reaction in a confined pocket, substrate and catalyst, they can actually organize in a specific manner, leading to the formation of one particular enantiomer. So our next target, and I think supramolecular chemists can target to mimic the concept that nature gifted enzymatic catalysis, in same way to do enantioselective organic transformation in confined pocket to get extra advantage of selectivity to form one particular enantiomer. So that is challenging, and of course separation of enantiomers from a racemic mixture by cage compound also is important. So overall, supramolecular chemists actually approach in a different way to resolve many things. I think catalysis particularly towards enantioselective. Moreover, many CPL activity nowadays is coming up, so you can design a chiral cage and inside that you add simple achiral fluorophore. In chiral environment, that achiral fluorophore will act as a chiral species. So fluorescence, so CPL activity can also be generated. So many things can be explored in future.
So one final advice you would like to give all young students?
Okay, so don't try to think everything in a complex way. Don't eye for very big molecules, very complex problem. Just read textbook, your undergraduate level standard textbooks, and get idea from that. I still do. Whenever I need idea, I just go back and check my undergraduate textbook to get many simple chemistry that people know for several decades. Let us see in a non-conventional way. Is it uniformly true, or it can be changed, or it is different if we do in a different way? So that is what you do. Still you will get new information, new results, and challenging problems. So my advice is, think in a simpler way to study chemistry, and then of course don't go follow the path that 100 people are following. Better you have your own pathway and work on simple problem in a non-conventional way. Then of course you will end up with unusual and interesting result.